Hello, this is lecture 20, stat 135. This is the last regular lecture on Bayesian statistics. Today we're going to cover section 8.6, Bayesian approach to parameter estimation. We started with a quick review of Bayes' rule and the beta distribution, and gave a quick overview of the frequentist approach, in which we treat our parameter as a fixed constant known only to Tyche. We develop some data and create the likelihood density, from which we find the theta that maximizes the likelihood density. That's called the MLE, or we use the likelihood density to compute moments to compute moments and use that to find the MOM estimate. Those estimates are random variables for which we can calculate the standard error to get some sense of variability for these estimates. In the Bayesian approach, we treat the parameter as a random variable, and we have a prior density, which is the density for that random variable before we've collected any data. And we're going to update that once we get data by writing down a likelihood density and then ultimately a posterior density using Bayes' rule. It's important to note that the denominator in this Bayes' rule formula here isn't something you hope to calculate, because it's just a constant. And what we hope is that by multiplying the likelihood and the prior, that we'll be able to recognize the variable part of that as some known density. And once we recognize it as a known density, gamma, beta, exponential, whatever it is, then we will know what that constant of integration is to make it integrate to 1. So that's the plan. So the important takeaway is that the posterior is proportional to the likelihood times the prior. And whereas the prior tends to be some broad distribution, the posterior is narrower or sharper, because once we collect data, we have less variability. We have more certainty in what value theta is most likely to take. So that brings us to our posterior mean, which is going to be our Bayesian estimator, which is simply the expectation of the posterior distribution. So the expectation is the center of the posterior distribution. So the expectation of the posterior mean is just the expectation of the parameter itself, and that's by property of iterated expectations. Example. So let's say that you flip a coin 20 times and you get 13 heads. What can you say about the probability of having heads? So in the frequentist approach, we find an MLE and we get 0.65. In the Bayesian approach, let's say we start with a uniform prior, and the number of heads is just binomial, so our likelihood follows the binomial formula. And then we take a look at the posterior, which is proportional to the product of those, which turns out to be beta. And we can see it's beta 14.8, and we know about the expectation of beta, so we can calculate what the posterior mean is. And here is a picture of the posterior distribution, beta 14.8, and the posterior mean is the center of that distribution, 0.63. Now, before we collected any data, our prior was uniform, and the posterior mean in this case is the center of the uniform, which is a half. We collected some data, and our posterior now looks more narrow, pointed, right? So that's what we're looking for. So let's say that we perform the experiment again, and this time we get 8 heads. So what we're going to do is we're going to make our posterior from before our new prior, and we have a new likelihood as well, reflecting the fact that now we have 8 heads. And so I asked you to find the posterior density and the posterior mean, and you can calculate the posterior density by just recognizing the variable part of the posterior density, which is this, right? That's the variable part. So that leads you to see that it's going to be beta 2220, and you know the density for beta 2220, so you can calculate the constant part. So you just know the constant part without having to calculate it. And then we can see that the posterior mean is 0.52. Now, when the prior and the posterior belong to the same family, in this previous case, both beta, because the uniform is beta 1,1, we say that the prior and the likelihood are conjugate. Okay, so when we have conjugate priors and likelihood, then it just makes this, it makes it easy to update the prior as the previous posterior, and sort of to cycle like we were just doing in the previous example. Okay, so gave you another example here that I'll let you just read, and then we came to take a break. Now we're back from our break, and I had you do an example where our data is Poisson. We have NIID Poisson, so that's our likelihood. Our prior is gamma for a fixed alpha lambda, and I asked you to find the posterior mean, to find the posterior mean for large N, and asked you whether the prior and the likelihood are conjugate pairs. So to compute the posterior distribution, you need to find the likelihood. So the joint likelihood is the product of the individual likelihoods. So we have a formula there, and you can just ignore the constant part of that. Putting that together with the gamma, you can see then that the posterior is going to be gamma, and then you can calculate the posterior mean. Now, for large N, N will be much larger than lambda, so you can just ignore the lambda. And for large N, the sum of the xi's, now xi's are non-negative numbers, that will also be much larger than alpha. So in the limit of large N, this will approach the mean of x. And we can conclude also that the Poisson and gamma are conjugate pairs, since the prior and the posterior were both gamma. I gave you another example here, but I don't really have anything to say about it, so I think I'll quit now.